Hi, everybody, and welcome to Physics 10. Today is April 8th, and I know this is the day before spring break. So hopefully you guys who are not live, we're going to go through the recording also and answer all the prompts about it. We have two topics today. They're not really 100% connected, but because one topic is kind of light, if we do it, probably we'll do it in 20 minutes or so, and the class will be over, and I really didn't think that was a wise thing. So we have two topics. The first one is on sound or musical instruments, to be more specific, which we're going to do it quickly. And then we're going to move into, because a lot of the ideas in musical instruments are already covered when we did the sound. There are some specifics when it comes to, for example, tuning devices and the terminology used in musical instruments and things like that. And also we're going to get into electricity and especially the first part, which is the electrostatics, namely charges not moving, which is a very, very important topic, especially when it comes to exam, the second exam just before the final. So which is an important topic that we need to get covered. Okay, so let me share with you a screen. So this is the topics of the day, namely, first of all, the first part, as I said, there are two different kinds of topics in here today. The first topic has to deal with the noise in music. And we talked about the harmonics, basically, when we were doing standing waves and the number of notes and NT notes. That is actually in here. The pitch, which is the frequency of sound, and how is that different from one frequency to the next. Sound quality and loudness, because again, due to interference, sound quality starts to deteriorate. So you'd want to sharpen basically the sound by making less and less of those interference, basically patterns. Loudness and the intensity. There is a unit that is used for sound. It's regardless of whether or not it's used in music or used anywhere else, and that is the decibel. And you probably heard that. The decibel is a unit which is a logarithmic scale, because our ears have a very, very wide range of sensitivity to sound, in the sense that we range from the very, very, very faint sounds, namely in terms of their intensity, to the super loud ones that they can trigger pain in the ear, because they start to become so violent that the ear starts to be moving too much out of its own, basically, the eardrum, that is, and it could lead actually to rupture. It could lead to damage to the ear. So that is basically how sound is measured. It's measured in a logarithmic scale because of the wide range of it. So the intensity really is power per unit area, in a sense that if you are very close from the source, usually it's louder. If you are very far away from it, it's going to be weaker, because the intensity drops with distance, like 1/distance squared, as a matter of fact. So that is the actual measurements. So the whisper, or the onset of sound, has a specific intensity when it comes to that. And the loudness comes with a different intensity. And to keep the numbers actually on a workable scale, it's a good idea to use a logarithmic scale, just like when they use the seismics, for example, effects of earthquakes. They use also a logarithmic scale. The difference between a 6.0 earthquake on the seismic scale versus 7.0 is not just 1 degree higher, it's actually 10 times more destructive, because of the logarithmic scale. That's exactly how we're doing it here. The quality of sound, again, depends on the interference, musical instruments, and Fourier analysis. Fourier analysis is basically when you take a signal and you break it down, its harmonics, the different components in it, okay? And we're probably going to talk a little bit maybe on DVDs, okay? Now that technology outdated at all, because now the onset of cloud storage that everybody now is using, actually streaming things online. Anyway, again, noise is when you have a lot of basically frequencies mixed up, and more or less it becomes kind of, you cannot really make out the clear tone or clear frequency in it. So you cannot see exactly the clear message. And it's usually a mixture of variety of frequencies in this case, so it's very hard to distinguish the one frequency from the next. Sometimes it's called white noise, okay? So that's basically what that is. Now, One that has less and less of it, a clear tone in this case, is that yes, you still have, because no matter how great the source of sound is, there is always that additional sources of sound that can make this not exactly a harmonic, not exactly a sine or a cosine function. That's what I mean by cosine, by a harmonic. Harmonic is either goes up and down nicely, like the figures we saw when we were doing waves. Okay, those are ideal pictures. Realistic ones, they usually have other frequencies built in here. So there is an overarching frequency in this case. You can clearly see it from here to here. That is actually a wavelength or a frequency if it's on the time scale. But there is another one in here that seems to be from this one is max to here too. So this is a higher frequency high, and this is a low frequency. So obviously the low frequency dominates because it looks like this is its intensity, but the low ones also appear to be there too, okay? And there is actually another frequency in here, or at least it seems like it's carried by the other one, okay? There is a sum of two frequencies in here. But in this one, it's too many. You cannot actually, there is a big frequency that you can see, but that is not even a clear frequency, because from here to here, probably there is a repetition, but then it comes from here to here, it's a different tone, and it's different completely. So many frequencies in here, you cannot even tell. Between this and this one, there is another frequency in there, and there is another one in here. So there is all kinds of frequencies in here. There are at least about 3 or 4 that I see in there. So that's why you have noise in here, and this is less noisy signal. So again, the pitch is the frequency, basically, determined by frequency of sound waves as they are received by the ear. The intensity is how loud they are. So somebody could be whispering and you barely hear him or her, but somebody could be very loud and you can hear them. Obviously, the person could be as loud as he or she wants to, but if you're far away from him or her, you're going to have a low intensity. So distance matters when it comes to intensity. So it determines the perceived loudness of sound. So it's perceived, not the actual one. The one that is coming out is the one that is the intensity, okay? So that is how loud it can be from the source. But then as it propagates, it starts to go less and less with distance. Case in point, if somebody stays a mile away and you try to call them, probably they will not be able to hear you. If they do, they must have very, very good, basically, hearing capabilities. Anyway, musical, there are 3 qualities for the 3 tone. There are 3 characteristics. The quality determined by prominence for of the harmonic, determined by the presence of relative intensity of various partials. In other words, this is what the quality in this is, determined by the prominent one. The prominent one is this frequency, okay? So this is how good it is. And also the quality is determined by the lack of, or at least least interference, the least intensity of the other frequencies. Okay, the pitch. Music is organized on many different levels. Most noticeably are musical notes. And those are the notes, do, re, mi, fa, sol, all of those, okay? Obviously, I really don't know a lot about the music. The way I know it is through the physics part of it. So if I'm not saying it correctly, I apologize, okay? But the frequency, I know what that is, and how to differentiate every different note, it has to do with that measurement of the frequency. And frequencies, actually, they come on different harmonics too. And the harmonic in this case, they are multiples of the original ones because of the standing waves that we saw last time, okay? And I demoed those for you guys. So again, these are the notes that are A, B, C, D, E, F, G. And I don't have my tuning fork in here again. I did not look for it. I apologize, okay, for that. And usually it has the note on it. I have the C note actually in there, but I don't see it anymore. Anyway, so again, these are different frequencies in here. You have 37, 32.7, 62. So let's check the ratios in here. Can I get my calculator quickly? Oh man, I turned it off. Sorry about that. Let me get my calculator quickly. What I'm trying to do is find the ratio of these different frequencies to see if they are harmonics or not. So what we have in here, let's start from the highest to from the second, actually, 65.41 divided by 32.7. The ratio here exactly 2 times. How about C3 over C1? C3 over C1 is 130.31 divided by 32.70. That is 3.98. That is 4 times this frequency, this fundamental frequency. So it must be twice as much as this one. It's clearly, you can guys see that's 130 is roughly 2 times 65, okay? 261 is roughly 130 times 2. As a matter of fact, 130.31 is, when you multiply it, it's very close from 260. So it's twice this one in here. 523 is roughly 2 times 261. So we're going in increments of 2 from one note to the note to the note to the note, and here on this scale, as we can clearly see. Multiply the frequency on any note by 2, and you have the same note as you have in there. The ratios, they're a little off again, and that is because typical pianos have this kind of ratios on them. They account for the tension, the length, and all of the other properties of every different note in here. So these are the different notes, and the sounding, of course, they are different. So this is what I meant by harmonics. Harmonics, the frequencies are multiples of one another, okay? So this is the C. Same thing is happening for the B note, and the same thing is happening for the A notes, and so on and so forth, okay? That's why they are grouped this way. So again, this is a high frequency, and again, depends on the instrument itself that is producing it. An wide open one will produce a low frequency, long wavelength in this case. Sorry, long wavelength, yeah, low frequency, short wavelengths, high frequency. So what I said before is correct. So high-pitched sound can be as high as 4,000, but we can hear up to 18,000. Actually, the range is usually between 20 to 20,000 hertz. That is our hearing basically range. And it depends on age too. As you start to age, your hearing starts to deteriorate little by little, okay? The intensity, as I was saying, is measured in a very wide scale from 1 watt, that's the power, 1 watt per square meter. Again, depends on how far you are from it, to 10 to the negative 12 watts per meter squared. That means, remember, if you convert this one back to pressure, this is a very, very tiny change in the atmospheric pressure. The atmospheric pressure is a huge one. And when you express the intensity of sound in this case by the power, and the power is proportional to the change in pressure, actually, in this case, square in the pressure. So what happened in this case is our onset of hearing, like the threshold of hearing, this is the pressure with which you're going to hear. You need this much. If there is a sound that has less intensity than this one, our ears, normal ears at least, would not be able to pick it up. So this is the whisper or the threshold of hearing. Compare that to 1 watt. 1 watt is really a siren or a nearby. That's a very, very intense one. This is a very bad intensity, 100 watts per square meter. That is too much intensity. If you stand there too close from it, so this is just like 30 meters away. If you are very close from it, 30 meters is not far, by the way, you're going to be hearing a lot of noise, and it's really deafening. And if you stay there an extended period of time, that is very, very deafening. So what you do in this case, you divide this numbers by this one. When you take 1 and you divide it by 10 to the negative 12, the ratio is 10 to the positive 12, because the negative go upstairs, it becomes positive. And you take the log in the base of 10. When you take the log in the base of 10, you drop the exponent, that's all. So in this case, it's going to be 12. By definition, we multiply that number by 10. So it's going to be 120. This one is going to be 120 decibels. If I compare this one with the disco, which is still loud, by the way, music amplified, So in this case, it's 10 to the negative 1 divided by 10 to the negative 12. So it's going to be 10 to the positive 11, because negative 1 plus 12 is positive 11. 11 times 10, that's 110 decibels, and so on and so forth. This one is 10 to the power 2 divided by 10 to the negative 12, which is 2 plus minus 12, which is 2 plus 12, and that is 14. When you take the log of 10 to the power 14, it's just 14. Don't forget to multiply it by 10 to get 114 decibels. So the scale in decibels, the sound level in decibels, is from 0, because when you take 10 to the negative 12 divided by 10 to the negative 12, that is 1. And if you plug 1 on the calculator and ask it what is the log of 1 in any base, it doesn't matter, base 10 or any other base, you're going to get exactly 0. So instead of talking this powers and the intensity in watts per square meter, we're going to use the ratio in here versus the threshold. How big it is compared to this threshold. That's all, number one. And take the log, and to have a number that is manageable. If somebody says, hey, they're talking 70, 60, 65, that is normal conversation right now. This is the normal sound. Unless you have your speaker extremely high or extremely low, which brings it to probably 40 if it's low, or maybe 70 if it is high. That's normal numbers in there. Okay, so this is normal. The thing to remember about the logarithmic scale is, if you change small jump, it is not, there is a lot of difference between it and actual sound. 10 decibels from here to here, this is a huge number. This is you want 10 steps, basically 1, 2, 3, 4, 5 steps. Actually, on the logarithmic scale, you went 10 times, because remember, you have to divide these numbers by 10. So the actual, if you don't include the 10, it's 0, 1, 2, 3, 4, all the way to 14. So when you jumped from 60 to 70, you went only with a power of 10 in here. So that's why the usefulness of the 10 in here. It's giving you exactly how many powers of 10 you want. But it's a useful scale. From 0 to 140, you have an idea. For example, it's like the temperature. If the temperature is 78, you know it's comfortable. If the temperature is 102, you know it's not comfortable. That's the same thing. Okay? So this is the advantage of using this scale for the intensity. So again, the intensity can be measured with, because it's actually it's a relative value. It's not an absolute value in here, because we're comparing it to some sort of a value in here that depends actually on the people too. So this is on average, because some people, they have different thresholds. So that's why it's subjective. It's not really okay. And again, this frequency also depends on the different people in here. Different instruments will produce different sounds for the same note, by the way. Okay, so this is actually time depends on that. This is the standing waves, the one that we were talking about it. If we keep everything the same, this frequency should be twice as much as this frequency. And this frequency should be twice as much as the fundamental frequency. This is called the fundamental frequency. This is actually the first excited, which is the second harmonic, the third harmonic, and so on and so forth, okay? Oh, there is all kinds of composites in here, which is a combination of the first, this one, and this one, okay? Composite vibration. Okay, again, I was talking about the signals in here for different instruments probably produce different frequencies, and this is fundamental. It has to do with internal mechanics, basically, of it, and different frequencies are picked up. And that's because you have a lot of moving parts in each and different one of them, which that's what really the essence of the Fourier analysis. When you do the Fourier analysis, you're going to find the fundamental frequencies of all of these signals, okay? And then you have the membrane. This is all of them are based on the string, basically behavior, but you have the main membrane like the drum, which produces actually two-dimensional shapes, actually two-dimensional standing waves on them. Electronic instruments, they use actually electricity and magnetism, and they produce actually signals that are a little bit different in a sense that they're actually bound only by the circuitry that you have, and sometimes they sound different than the mechanical instruments. And some people with nostalgia, they prefer apparently the mechanical of this. That's what they hope to see because of the quality. The Fourier analysis is how to take basically a different signal and break it into its own component in terms of its harmonics. Fourier analysis is a very powerful mathematical tool used to take a signal, it doesn't matter which one, and you break it into its component. This is actually a very essential technique, not just used for music, but it's used everywhere there is a periodic phenomenon, and you would want to analyze it to find the fundamental frequencies that it has, because sometimes this behavior can lead to some other unwanted behavior, like, for example, violent vibrations or even chaotic behavior. So this is usually very important technique used for whenever there is a periodic motion, including in this case, since we're dealing with waves, which usually has a lot of harmonics and frequencies in it. Again, the Fourier analysis is really a mathematical tool, and you start breaking your signal into different frequencies. There is, for example, this frequency with this much intensity. There is another frequency that you see here from max to min, from when it repeats. Crest to crest is different than this one, crest to crest. So this one has a higher frequency. This one is even a higher frequency or less intensity. So when you add them up, you will still have the dominant frequency, which is this one, because of intensity, that's all. But the others are present in there, and they express themselves through this changes in the signal. So this is just a 3 frequency composition of the fundamental ones. And you can do analysis like this one to check if your signal, how good it is, and how you can make it, which frequency you would want to amplify and which one you want to get rid of, and so on and so forth, okay? Okay, so this is enough about sound waves and everything else. So let's get into electrostatics, because electrostatics is a big deal in here when it comes to the next section of this class, and we really have to get it covered, okay? So the question of the day is going to be about this one in here, okay? So all of you guys have experienced this phenomenon, okay? When you are probably walking on carpet, for example, and your feet are rubbing against the carpet, and you touch the doorknob, for example, or you touch your friend, you feel that shock. That is electricity. Or you have seen the lightning, and the lightning actually is electricity also. So what I have in here, I have a piece of paper. I set it on my phone, okay? And I'm going to demo, or at least try to demo this what we're talking about it right now. If I try to grab it, it's not grabbing it. So I have in here a neutral rod. I'm going to try to grab it, so it's not pulling on it. Why? Because the earth is pulling on the phone and pulling on the piece of paper. And the earth is a supermassive object. It has a lot of mass in it. So what I'm going to do is I'm going to take this towel, and I'm going to rub this on it, trying to scratch some electrons from it, okay? Trying to remove some electrons from the towel, and then put it on a piece of paper and see if it's going to attract the paper. Tries to come, but now it's neutralized. Okay, try it one more time. Because this is actually I touched the other one, so I lost it, okay? Make it slightly smaller and see if I have better luck with it. What we have in classroom, we have fur, I think from rabbits. And we have rods like this one, and we do the demo in classroom. Actually, you don't need this. You could take your brush, okay? And do this one with a brush after you put it through. I don't have much hair, okay? So I'll try it on my hair if I have some, but I don't. Sorry about that, guys, okay? Okay, this is the last chance. If it doesn't work, it doesn't work, okay? Hey, it worked at least for some time, okay? So the point being in here is that this is electrostatics or electricity, and it has to do with this phenomenon. the thing with it is, if you have a charge, you do this game. You can have electrostatic interactions like this one. What people did actually, they experimented with different masses after rubbing them and doing stuff like this one, for example, and you have a piece that is usually non-metal, which is like an insulator. You have charges on it, and you bring it next to the other one. I have a balloon in here. I used to have it. And bring them next to one another, and they become charged, okay? And then you can check the effects of the charge. For example, you take one charge, you divide it in half, and when you double the charge, what happened to it? When you take it by half, what happened to it? And they noticed that this force, there is a force, if they have the same sign of the charge, they will repel each other. The force is actually a repulsive force. When they have different signs, like for example, the towel I was talking about and the rod, they have different forces. They actually attract one another. So that is one thing. The other thing is, the more charge you have, the more attraction you have. If you have no charge, you don't attract and you don't repel. So what's going on with the paper? I didn't really scratch the paper. I didn't do anything to the paper. All I did was the rod. So in that situation, what's going on? There is an induction, which is actually a weaker force. The rod will induce a charge in the paper, and the paper now is pulled up for it. So it's still neutral, the paper. That's why it was very hard to push it, pull it up, because on one side it's a positive charge and on this side it's a negative charge. It's trying to attract the positive charge, but in doing so, it interacted actually also with the negative charge. So it did not, there is kind of competition between these two charges. Anyway, so this is actually how the force is. The other effect was the distance. The further the charges are, the weaker the force by a square. In other words, if you double the distance, the force drops by a factor of 4. If you triple the distance, the force drops by a factor of 9, because it's proportional to the inverse of the square distance, just like what I was talking about earlier about the intensity. Okay, so these are, in summary, what Coulomb's law is. Okay, there are two kinds of materials. This one is actually an insulator material. Where is the rod? This one is an insulating material. And then there is also another type of materials, like metals in general, they're conductors, okay? You have conducting materials and you have insulating. Insulators, they can actually keep the charge and put it wherever you put it in them. Metals, though, they have a weird thing because they have free electrons to move freely. They can actually disperse of the charge wherever there is a new connection. That's why this experiment doesn't work well with the metals, okay? So you have to have an insulator to have this experiment. And then there are other kind of materials. There is actually semiconductors, materials that don't really conduct well, but don't resist much either. So they are actually somewhere in between. With the proper doping, with the proper basically impurity added to them, they become good conductors. Sometimes of actual electrons, and they're called N-type doping. And sometimes they're actually, they don't conduct with the electrons, but they conduct with the lack of electrons, deficiency in electrons, because the doping takes actually some of the electrons that can move. So now they are basically anchored into those impurities. So what happened in this case is the missing electron that starts to move. It's called a hole, actually. And this is called a p-type doping. The P stands for positive, because the charges that are actually moving are not charges at all. They're actually vacancies, okay? And both of them, actually, the P and the type, N-type, they become important in semiconductors, and you can have all kinds of fascinating stuff with this thing. Every single device you have in your household is made up of, for the main part, semiconductors. Like this one in here, it's a semiconductor, actually. This is a diode. This is actually, you have the two junctions inside. The two junctions inside, and the two junctions, the P, the part P and the part N, they are actually inside of this material. And I don't know if you can see the coloring in there. And this is actually a diode that can conduct electricity. Each diode, if you have one at home, or if you happen to have one kit at home, has two legs, a long leg and a short leg. I cannot see it in here, okay? And this is basically how the diode works. It has two, basically, it can only conduct electricity from one side, and it's a complete, blocks it from the other side completely, okay? So this is a PN junction, and then you have an NPN or PNP, have put three of them together, and that is the transistors. So semiconductors are a fascinating topic. Unfortunately, they're a little bit outside of the scope of this one in terms of how to understand them, but they're good. Okay. The third type of material, the fourth type of material is superconductors. Superconductors are materials, they don't resist whatsoever the current. Any conductor, no matter how good it is, will resist current. So there is this finite resistance no matter what, okay? And if you don't believe me, take your charger, which is a good conductor made out of copper for the most part, put it charging your phone or plug it in anywhere and touch it after a while and you will find it warm. Why is it getting hot? It's because of the resistance that it has in it. Even though it's a good conductor, it still has a resistance. Superconductors, no, they don't do that. They're actually perfect conductors, no resistance whatsoever. The only trouble with it is they don't exist in room temperature. They're super low temperatures. We're going to talk about the charging and how you build charges and also the charge polarization. I already mentioned it with the experiment I did. In a sense, what's going on with the paper, and here you have it polarized, okay? You have induced a charge in it, okay? We're going to talk about the electric field, the electric potential, and the energy storage, okay? Because nothing matters really until you have energy. Like in this battery I was showing earlier, this is actually stored the electrostatic energy inside of it. If I connect the two ends now, current starts to flow from the positive side to the negative side. Inside the battery is going to move the charges again to the positive and the circuit will be completed, okay? So it's going to go always from positive to negative. So this is the positive always of the battery and the other one. So that is basically how this thing is. Okay, interesting stuff, isn't it? Okay. So electricity is a name given to a wide range of electrical phenomena such as lightning, spark, when we strike a match, okay? The spark, okay? Like when you take two rocks and hit them against one another. That is actually electricity, the flying things. And that. What holds atoms together is actually electrostatic force, electricity. Electrostatics involve charges, the force between them, the aura that surrounds them, and their behavior in materials. Again, this is the experiment I was talking about. Two like charges, regardless of whether or not they're positive or negative, they repel. Two unlike charges, they attract. So this is what we're going to be describing today in the item of discussion, the electrostatic force. So one property of the electrostatic force is like charges repel, whether positive or negative, and like charges attract, doesn't matter, both of them, they will attract one another. So this is item one. Item one is a comparison, or at least the properties of the electrostatic force. So this is one of them, okay? Nature has provided us with elementary particles. Some of them have positive charge. Some of them have negative charge. And the nature was so careful in choosing the exact same number for both of them. 1.602 times 10 to the negative 19 Coulomb. This is the charge of an electron, albeit it's negative. This is the same charge for the proton, albeit it's positive, but the values are identical. The mass of this guy is very tiny. It's about 1,860 less than this one, okay? Almost 2,000 times less than a proton. So the masses are not the same, but the charges are immaculately the same number. This is amazing, okay? That the two numbers, they happen to be exactly the same number, and this is one of the mysteries of nature. And it's good that it is this way, because atoms are neutral, at least if they don't have, on regular atoms, they are neutral. They are not, I mean, we're not talking about ions, we're talking about atoms. Atoms are neutral. And if atoms were not neutral, none of us can sit where they are sitting right now. Actually, none of us will exist, because if there is an imbalance one way or the other, we will have an excess of positive charges or excess of negative charges, and then everything was going to fly every which way. But because of the fact that, this fact that protons and neutrons have the same charge, but opposite sign, matter stays together. I mean, it stays next to one another, which means that the force of gravity dominates, which is super weak force compared to this one, but it's still it becomes important on a large scale, like for example, on the planet scale or the solar system scale or the universe scale. Otherwise, if there was an imbalance in these numbers, the numbers did not match exactly, forget about gravity. This force, the electrostatic force, is much, much bigger. As a matter of fact, this force is about 1 followed by, I'm not sure if I can be able to finish this number. So far I have 9 zeros, and I need more of this. This is, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm not done, okay? 13, okay? So this is how much this force, the electrostatic force, is bigger than gravity. So gravity is tiny compared to the electric force. The electric force is this much, 1 followed by 40 zeros. So I try to write 40 zeros in here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 times 3, that's 39, plus that extra 0. So it's 10 to the power 40 more powerful. I don't know how to read this number. I know this is 1,000, this is 1,000,000, this is 1,000,000,000, this is 1,000,000,000,000, this is, I don't know what that is. Starts from this point on, I have no idea. I mean, you can say it's 1,000 trillions and million trillions and billion trillions and trillion trillions and 1,000 trillion trillions and what is it, 10 billion trillion trillions or something like that. It's too much, okay? Anyway, because of these numbers, they are matching, this force cancels out, okay? Which leaves us now with the force of gravity that dominates. Thank you. Thank you, Miguel. Okay. I think they have actually not this number. They have another one. Is it a Google number or something like that? Or numbers that are 10 to the power 10, 10 to the power 10 to the power 10 or something, 10 to the power. I mean, this is ridiculous. I mean, it's too much right now at this point, okay? But the point being in here is, if nature did not come up with these two numbers that match for both the proton and the electron, we would have this force dominate everything, and either we cannot sit next to one another whatsoever. Nothing is closer to one another if we have the same charge, and we should then, because if we have the same composition. So nobody can talk to nobody. Actually, as a matter of fact, nobody can be nobody, because his or her parts will fly every which way, okay? So because there is a match in here, that this one. Neutrons, though, they are neutral charge. These guys, they are useless when it comes to this force. They don't care about this. These ones are, they don't play this game. I mean, they play another game, which is important, actually, nuclear force, to fuse this nucleus together. But that's another game, okay? But this game of electricity, these guys are not invited, okay? They're neutral. These ones, they play the game. They're allowed. These two guys are allowed in the game, okay? If you have a charge, you are allowed. If you don't have a charge, get out of here, okay? So that is how you can envision this. Force of gravity doesn't care. Force of gravity, if you have mass, and everybody has mass, so everybody plays that game. And that's why we have the universe held together. So albeit the gravity is super weak compared to this force, gravity will dominate when you have a lot of masses, because everything else cancels, and now is going to emerge, okay, as the winner, at least on a large scale. So again, every atom is formed from them. Each electron in an atom has the same quantity negative charge of the same and the same mass. That is another peculiar behavior also. It seems like every single electron, wherever it's made, whether it's made in a nuclear accelerator somewhere in Switzerland or made in the other edge of the universe via some sort of a supernova or something like that, it has the same mass and the same charge. This is one of the things that are kind of unique to nature. Okay. So protons and neutrons compose the nucleus, and each proton is about 1,800 times more massive than the electron, but each carries the amount of charge that's exactly the same thing. So atoms usually have as many electrons as protons. So on the average, they have 0. That's why they're ions, on the other hand, have a net positive or negative charge. If an atom loses 1 electron or more, then it becomes positively charged. If an ion gains 1 or more electrons, then it becomes negatively charged. Usually, the atoms on the far left of the periodic table, namely the metals and their likes, they lose electrons and they become positively charged. The atoms that are on the right of the periodic table, they gain that electron. They have affinity for electrons and they become negatively charged. Usually, and then this is a bit of chemistry, is that there are 2 kinds of electrons that are the ones that are inside the shells of the lower energy levels. No problem. No, there is no item yet. The biggest item, Samantha, is the fact that we're listing the properties. That is the item of the discussion, listing the properties of the electrostatic force. And the electrostatic force in here is related to the first thing that we discussed is like charges repel, and attractive forces, unlike charges attract, okay? So this is the first point of that item. It's only one item so far, okay? There will be more points in it. So this is properties of the electrostatic force. So we need to list that at the end of the discussion today. So one of them, item 1, is like charges repel, and unlike ones attract. Try to put your discussion sessions. I really honestly like it to be more verbose, more sentence structured, not like bulleted items, okay? You can say, for example, one of the characteristics of this electrostatic force is that like charges repel one another, positive or negative, and negative charges, unlike charges, they always attract. So this is property number 1. There are more properties coming for this force, okay? So this is not the entire picture. There is more coming. Okay. So again, we talked about the Coulomb. Actually, we talked about the experience in here. So you yank charges from it and it becomes negatively charged, okay? When you brush your hair and scrape electrons from your hair, the charge of your hair is, of course, it's going to be positive because you remove the electrons from it. So your hair becomes positive and the comb becomes negative. And the same thing in here, what I was doing earlier, or at least tried to do, is that with that rod, we were able to extract electrons from it that induced charge inside the piece of paper. So this is Coulomb's law. Mr. Coulomb actually did a lot of work, but his main contribution was he actually collected a lot of this work of everybody else in his time and before him, and he put it into a nice law, okay? That relationship among electrical charges was discovered by Coulomb, and states that charges that are much smaller than the distance between them, the force between them, varies directly as a product of their charges and inversely product to the distance separation. This is the other 2 characteristics of the law. This force, electrostatic force, is proportional to the charges and is inversely proportional to the square of the separation. So those are the other 2 characteristics. So like charges and repel and unlike charges attract, the force is dependent on the strength of each charge. The more charge you have, the stronger the force is. And the last one is that it's inversely proportional to the distance. The further they are, the weaker the force is. The closer they are, the stronger it is. And actually the square value, not linear fashion. So for example, if they are, let's say, for example, 1 centimeter apart, and you take for example, okay, depending on the charge and depending on all of that. So if you take 1 centimeter apart, and let's say, for example, the force is 1 Newton. Now, if you move them further away to 2 centimeters, you double the distance, the force drops by a factor of 4 to 0.25. Sorry, to 0.5. Yes, 0.25 drops by a factor of 4 if you double the distance. But if you bring them closer to a half a centimeter, then in this case, the force will go up by 4 times, 4 newtons. So the closer they are, the stronger the force. That's why the word inversely here is used. The further they are, the weaker the force, but not by any amount, by the square. So if you double the distance, the force in this case shrinks by a factor of 4. If you shrink the distance by a factor of 2, namely make it half, the force quadruples. That is basically what the statement is. So those are the other 2 characteristics of this law. As a matter of fact, algebraically can be written as follows. K times the product of the 2 charges divided by the distance squared. So this summarizes everything. Where K is just a constant number. K was chosen so that this force is actually in Newton because these charges are in Coulomb. So this is a Coulomb times Coulomb, that's a Coulomb squared, divided by distance squared, which is meter squared. So we need to fix this one so that it has to have proper units, number 1. Number 2 also is to match some definitions for the units in here for the Coulomb in terms of the ampere. That's where this number of 10 to the power 9 or 9 billion comes up from, okay? That's what makes this force super huge, okay? That's what makes this force super massive. That's what makes that number that I wrote in the beginning is this factor 9. Because the force of gravity is similar to this one, and the force of gravity due to Mr. Newton is g times the first mass times the second mass divided by the distance squared. Both of them have that distance squared in them. But here I have the mass and here I have the mass. But if I take the masses of the electron, they are 10 to the negative 31, for example. I just gave the number earlier. But the charge of the electron is only 10 to the negative 19. So it's much, much, much bigger charge, relatively speaking, compared to this number, which is 10 to the negative 31. That's one thing. The other thing also, G, if you guys remember from our discussion, is 6.67 times 10 to the negative 11. So this is 0 followed by point, and then you have 10 zeros before the first decimal point. And this one is actually 1 or 9, followed by 9 zeros. So this number is what makes the big difference compared to this one, in addition to the ratio of the mass to that of the charge, which is also make up for it. So that number that I put in there was not an exaggeration, it was actually an actual number. So the electrostatic force is much, much stronger. And the only reason we don't experience with it on a daily, actually we do experience with it. If you shake hands with somebody else, your hand does not go through it. The reason why is your electrons from your hand to the other hand they don't go through one another, okay? They interact with one another. Actually, they interact through a different mechanism, but they do still interact. It's the electrons that are responsible for that thing. The only reason you can see at all is because of the electrons. The only reason why you can hear at all is because of the electrons. The only reason why you're sitting still and not going through the chair and going through the entire Earth, going all the way to the center of the Earth, is because of the electrons. So yes, it plays a major role, but we don't have that much experience with it because everything is neutral. And that's really the advantage of it too. Okay, according to Coulomb's law, a pair of particles that are placed twice as far will experience forces that are, in this case, 4 times as much. I'm sorry. A pair of particles that are placed twice as far. Oh, I'm sorry, it goes down. What am I talking about? Yeah, it's 1/4. So they were here. And now you put them here. So this distance has doubled now to this much. The force will shrink by a factor of 4. So if this is what the force bringing them together, this is how much force now is bringing them together. Okay, so that is basically how you can think of this. So difference between gravitation. So you got the second point, guys. Okay. The 2 items of the first item, the 2 parts of the first item, namely that the electrostatic force has 3 properties. The first one, like charges and unlike charges and how they behave. And the second is the effects of a charge, which is the force is proportional to it. and the third one is inversely proportional to the square. So now we have another point in here that is the difference between gravitational and electrostatic force. Electrostatic may be either attractive or repulsive. Gravitational force is always attractive. Masses only attract one another, okay? If I have a balloon, we would have demonstrated this one, and we do it actually. We did it actually in a classroom, and this one stayed there for almost the entire period. At the end of the period, it starts to fall down. What's going on in here, we have an induced charge in the wall. So yes, you rub the balloon against, for example, a piece of hair from a rabbit or something like that. Usually it's a dead-skinned rabbit, okay? They bring them to the cottage, sometimes cats, actually. You rub against it, now you have excess electrons. When you bring it to the wall, it's going to induce a charge in the wall. So what happened in this case is that the wall is neutral, but the sides of its molecules move around in such a way that they give it the positive charge in here facing it, because this is the effect in here. This is the ones that are attracting. So they flip the different molecules inside the paint and make it turn around, and there is an attraction, and the balloon will stay in there. We're sitting there for a long, long time. Usually you have to be careful with the moisture though, because it plays a role in there. It's going to mess up your thing in there. But on dry water, it's going to work beautifully. Again, I mentioned conductors and insulators. Conductors are usually good conductors of electricity, like for example, metals, because they have free electrons. Electrons do not belong to a single atom. They are still neutral though. They are still neutral. Like this, for example, this metal, the iron, this iron in here, the electrons in it are still the same number of the protons, and it's still neutral. But if I place an electric field in here through, for example, a battery, the electrons start to move and actually starts to warm up this one, and I can feel it from the motion of the charges. An insulator like rubber, for example, or glass, or the air, which is an important insulator, is an example of an insulator. It's very hard to move its charges because the charges belong to the entire, each atom. Each atom holds its own charges. If the air is not an insulator, but a conductor rather, we have a problem, because we have plugs in our households, and those plugs, they have charges in them because of the difference in voltage. Each household has at least many plugs, each one of them, there is a difference of potential of around 120 volts. So those are chargers ready to move. The minute you plug in your device or charger, for example, the charger starts to move because there is conduction. Otherwise, they're waiting to be moved. Like this battery in here, it has a net positive charges on this side, and it has net negative charges on this side. As a matter of fact, what's going on with this specific battery in general, because you know that the protons are inside the atom, and they are very hard to move. What is moving in this case are electrons only. So what's going on in this case, there is an excess of electrons in this side. The battery moved them there, depleting this region of its electrons. So there is a lack of electrons on this side, meaning it's positive. But on this side, there is an excess of them. So if you take a wire and you connect it to the other side, to what's going on in here, this electrons in here will move to cancel these charges. But because a battery is a good battery, this battery operates at 1.5 volt, and it still have juice in it. So it's going to do, the minute one electron shows up in here, it's going to drag it to the opposite side. It doesn't want to be on this side. Why? Because there are negative charges already here, and it's happy where it is. There are positive charges in there, and it cancels them. But the battery has power, has a secret, which is its electromotive force. That's what you pay for when you go to the store. What you're paying for, that chemical process to drag the electrons from this end where they really want to be to the end where they don't want to be. Now you have a lot of them sitting in here. So if the wire is still connected, again, they will go through the wire and come in here. The minute one of them shows up in here, the battery will drag it to the other side. And it's always doing that. Okay, until it runs out of juice, in which case you have to go and cough up more money, basically, for another battery. Okay, so that is really how batteries work too. That is how electrical conduction happens actually in a circuit. So this is how circuits work. We're going to get into this, and I'm going to demo circuits for you guys. Again, I mentioned semiconductors, and I actually went into a lot of detail with them, more than I probably should. But they're a fascinating topic because of the fact not a single device in your household, especially many electronics, can operate without this ones in here. Okay, without the semiconductors. Semiconductors is really what is a revolution in the 20th century. This is a good example in here. When you go to the hardware store, when you go to Home Depot, for example, or Lowe's, and you tell them, you know what, I want a conduit for the water. I want to fix the pipes in my home. They sell you the pipe, but they don't sell you the water. It's the water company that is supposed to provide you with the water. But if you tell them that you would want copper wire to be plugged into your wall, for example, or trying to do something with it, they will provide you the wire with its electrons. It comes ready with the electrons. So what's going on in the battery in here when you take this wire and connected it, and I really don't want to discharge it. So if you connect this wire from one end and you go to the other end and connect it, the electrons are sitting in this wire. So, and there is excess of electrons in here. So all they do is just push this electron, which pushes another electron from the other end. So the battery is, all it does is just replenishing the electrons, basically, that's all, because they're being continuously pumped. So when you remove the wire ends up back neutral, end up back into its charges, the way it was before, okay? So, and the battery stays with its charges. So what the power company does to you in your household, it does not provide you with electrons whatsoever. You have to bring your own. It provides you with a difference in potential. The minute one of them ends in 1, because usually there are 2 holes, the third one is, if there is 1, it's for other purpose, okay? Then in this case, it's going to take it and push it to the other side, and that's it. So that's all it does. That's all what the difference in potential does, like a battery, really. Superconductors, as I mentioned in there, is that the electricity will flow with no resistance to current. The phenomenon is very hard to understand, especially without quantum mechanics, because what's going on in this case is that the electrons, they will pair with one another, and in doing so, because of the low temperature, extremely low temperatures, the ions where normally the electrons will pair through, will collide with to produce the resistance, are barely moving. So what happened in this case, the electron comes through a pair of ions through the atom, basically the 2 atoms sitting. So it will attract it and the other one repel it. So in this case, they take advantage of that, and the pair of the electrons move through unimpeded with 0 resistance, basically. And that is what superconductivity is. It's used nowadays, although the temperatures are very low. It's used for trains in Japan, for example, for the levitation. And it has a lot of applications in science. We're waiting for the day when room temperature superconductors are available so that we can deliver power with 0 loss. That would be amazing, because then the power will be basically available for far more, because a lot of power is lost during the process of transport, and actually during the process of using it. Every device you leave it plugged into the wall or turn it on, and you feel a lot of heat coming from it, and that is the resistance, and that's waste energy, actually. So it's a really promising thing, except that at this point, the problem with the technology is still too low for temperatures. Again, I mentioned, actually, I demoed how you charge and how you create a charge. In the case of the battery, it's a different process altogether, but then you end up with the charges, and you can put charges actually on capacitors, on different plates, on metals, and things like that. In the case of the clouds, again, the clouds in this case, they rub against one another, just like the one that I demoed earlier with which is really a very, very poor thing, which is a towel. If I had skin of any dead animal, probably it would have worked a lot better. That's why I miss a lab too, because we have a lot of stuff that we can do in here. Again, because of this friction, charges are built up in this case, and there is separation. There is lightning on both sides, actually. And this is induced charges from the ground, actually. They're not really, because the Earth is really an infinite reservoir of charges. So this charges, the negative charges, just like the balloon before, okay? They will induce charges on this side, and that's if the charges are too much, the electric potential will be too big. That could lead to the dielectric breaking point, which is in this case lightning. And remember, the air is an insulator, but even the air can become a conductor with a very high enough voltage. And that is really where the lightning happens. Again, you can charge one, bring a negatively charged next to the balloon. So at neutral right now, these are conductors usually, okay? Bring it to one side. Now you induce the charges to move one way, separate them, and now you have effectively two charges. And you can take this one and contact it with another one that was neutral, and you split the charge in here and so on and so forth. This is one way of getting to test this theory. And the polarization, basically what's going on in here, you bring a normal charge has, everything is canceling. In this case, you have in this case, an atom, where you have the nucleus has a positive charge, and they have a cloud of negative charges, and the distribution is symmetrical, which means that there is no net charge one way or the other. But when the distribution is asymmetrical, then in this case, there is a net charge on one side, then a net negative charge on the other side, and this is what the dipole is actually. You have two different charges sitting next to one another. And so again, you can induce charges like what happened in the wall when I was talking about that. That's an example for that. And this is actually what happened with the comb. Also, you can induce charges in the piece of paper, and that's what attracted the piece of paper earlier. Although I did it with the and this is the same phenomenon that we talked about, the charge induction in here. Well, polarization is a very important aspect of not just for this electrostatics, but for the case of stability of molecules. This is how water actually is water in room temperature. Water, if you think about it, is a lot lighter than carbon dioxide. Carbon dioxide is made up of two oxygen atoms, which are heavy. Each one of them is 16, basically, nucleons, 8 protons and 8 neutrons. So you have 8 and 8, which are supermassive, that's 16. And you have 2 of them in the carbon dioxide. So that means a total of 32 ions, 32 nucleons, I'm sorry. Plus the carbon itself is not light, it's 12. Basically, it has 6 protons and 6 neutrons for a total of 12. So altogether, you have 44 nucleons. Compare that to water. Water has oxygen, yes, it's heavy. It's one of, but the other one has 2. Carbon dioxide has 2 oxygen, not just 1 oxygen. So the water has 1 oxygen, but it has super light. The lightest element in the periodic table, which is hydrogen, it has only 1 proton. Now you have 1 proton, but you have 2 of them, that's 2. Plus the 16 from that oxygen atom, now you have a total of 18. Compare that to the 44, the supermassive of carbon dioxide. But carbon dioxide in room temperature, normal temperature, it's gas. And water in normal temperature, H2O, is liquid. So, and actually the gas in this case will float, and the liquid will come to the Earth. So despite of the fact that carbon dioxide is a lot heavier than water, at room temperature, carbon dioxide is gas and the other one is not, is liquid. And it has to do with the polarization of the water. Water is a polarized molecule in a sense that water has 1 net charge on one side and another net charge on the other. So one water molecule and another water molecule, they flip one another, and basically they will pull on each other. They stick together. Whereas a carbon dioxide is non-polar, does not have any polarity. So carbon dioxide, basically, if you put 2 carbon dioxide molecules next to one another, they're completely unaware that they are existing next to one another. That's why it's gas, because there is no interaction between neighboring atoms, neighboring molecules. Whereas in the case of water, there is an interaction between the neighbors and becomes liquid. You really need the temperature around 100 degrees Celsius to have this water molecules agitated enough with a high temperature so that you break that bond, and then it becomes just another gas. It becomes vapor, actually, vaporizes. Okay? So it's an important aspect, and it really explains a lot of things, this polarization. So molecules are more polarized than others. So what causes it? Causes it is really usually an asymmetry in the distribution, like this one in here. There is an asymmetry because, first of all, the oxygen has more protons inside to attract more charges to it, and it's more massive. So in this case, it's going to attract towards it. In the case of carbon dioxide, for example, since we stick with this example, you have an oxygen atom which is big compared to a carbon atom which is smaller, and it's probably trying to pull more on the electrons of the carbon that are shared on this side, but there is another oxygen on the other side that is going to be equally pulling on its side. So now you have one oxygen pulling and the other oxygen is pulling, and the net effect is they cancel each other. And that is because it's a linear structure, actually. Whereas this one has this shape of 102 degrees, actually, between these two hydrogens. So there is an asymmetry, and the asymmetry is actually along this axis. And that's why the charge is along this axis. Okay? How are we doing on time? Which brings us to another key concept in here, and that is the electric field. The electric field is how space is changed by the presence of a charge. Because here is the deal. If I have a positive charge in here, or a negative charge, where is my pen? If I have a charge in here, okay, positive charge. And let's say, for example, I have a positive charge also. So this is Q1, this is Q2. And if I attach this Q1 to a spring and mass and measure the force, so this spring will expand, will compress actually, because both of them have the same sign. The charge is moved this way by this force, which we calculated to be Q1 times Q2 divided by this distance squared, this distance actually, divided by this distance squared times that number of 9 billion, okay? So this is how much force. So let's do the following. Let's move this charge here. Move it away. Obviously, the spring will relax a little bit because now this mass has moved slightly further away. So the force will be less. So because this charge has moved further away, this distance is a little bigger. So when you divide by the square of it, it's going to be even less. How does Q2 know? How does the spring know that this charge has moved? What if we kill this charge? What if we remove it completely or neutralize it to do something to it? This will relax completely. And this will reach 0 Newton if we do that. How does it know that? If we bring a positive charge instead in here, and we charge it to become a positive, negative charge, not only is it going to relax, but it's going to actually stretch. And it's going to stretch by the right amount, depending on the distance and also that. How does it know that? Is somebody telling it? Is there like a secret messenger between the two? Hey, I changed, okay, fix your value of the force. Hey, I'm no longer here, okay, bye. I'm changed color now. I used to be positive, now I'm actually negative. You're going to come closer now, you're too far. How is that communication is happening? The interpretation for that is through the field. Whether you have this charge here or not, this is a test charge, of course. Whether you have a test charge here or not is regardless. So what's going on, a charge in here, positive or negative, let's take it a positive step, will change its environment depending on where you are in space. Provided, of course, you're going to nail it, okay? We're going to fix it. We're going to bring nails and a hammer and fix it in place, okay? And give it time to do what it needs to do, basically. So if I bring this mass in here, I mean this system in here of test charge, and put it in here, what it's aware of, it doesn't care about this charge. What it cares about is the value of how the space has been changed in here. And that is the measure of that. That is the measure of how much space has been altered by the presence of this one. So if I make it closer, it doesn't care about that charge. All it cares about how space has been altered by that one, and so on and so forth. So if this one has been removed, the space is going to change accordingly. So the value in here will change accordingly because that's the electric field has changed. So this is the explanation for it. Charges behave like water faucet and a sink. This is like a sink. The electric field is going into a negative charge. That means my positive charge, the test charge in here, will be attracted in here. Wherever I put it, it's going to be attracted to it. Okay? If I have, on the other hand, a negative charge, it's going to be repelled there. So if I put a negative charge in here, it's going to move away and so on and so forth. So what we say in this case is that positive charge is like a source, like a faucet, and the negative charge is like a sink. Okay? One of them is a sink and the other one is like a faucet for the electric field. And then the charges now, my test charge will follow which way the field is pointing. If it is a faucet, it's going to move away with the flow. If it is a sink, it's going to fall into it, and that's it. And the electric field, again, can be produced in here by the Van de Graaff machine. Usually we have, I think I have seen it. We have one, actually, I have seen it. Hopefully when we go back in session, we'll do a science line out and you guys can come in here with your hair and experience in this case. So what you do in this case, you build a charge on it. So on the Van de Graaff, there will be a lot of charges in it. So the minute you touch it, and you have to be insulated in the bottom. Otherwise, you're going to be electrocuted. You don't want that. You're going to be too much charge. So you're going to be insulated. And then you're going to put your hand on it and the charge will transfer. And actually, you can feel it in your hair. And it's a kind of sensation that you're going to have in there. But if you have long hair, you're going to see your hair going every which way. Obviously, I will be a very bad candidate for it because of my hair. Okay. It's not going to work for me. I mean, I will feel it, but probably you will not see my hair go like crazy like this one, okay? Again, the electric potential is really the idea behind it is that is the one that I was talking about, the voltage. The battery has a voltage and it's an energy and you store it in the electric potential and that's what you buy from the store. And it's similar to the mechanical energy in this case, okay? When you release charge, it's going to be attracted to those. So there is energy in here. In other words, if you have a positive charge and negative charge and you push them away, you need force to do that, to maintain them at that distance. If you let go of it, it's going to fly in. Same thing, if you have a negative charge and a negative charge or a positive charge and a positive charge, in order to put them at this distance, you really need to work against the electrostatic force. If you let go of it, it's going to fly away. That is where the electrostatic energy. In other words, you're going to get kinetic energy out of it. And this is a similarity with the spring system in here. This is the second item in here of discussion, which is a very important item, is that the electrical energy is the charge times the electrical potential. You really need to know this relationship because you plug in your device, it has 120 volts. Okay, that is how much the voltage is in there, in the plug in the wall. Now, how much the company will charge you, how much the power company will charge you, it's not based on the fact that you have 120 volts in your home. That they will provide, and every single plug is the same plug, 120 volts in your household. How much they're going to charge you, depending on how much charges you actually take. Okay, consume. They have to push through the wire. That is what you're going to pay for. So this is item 2. Okay. Again, this is just an explanation of the same thing. Energy is in joule.
So,
Sorry?
what was item 2?
Item 2 is the fact that the electrical energy is the product of the charge and the electrical potential.
Okay.
Okay. So I'm trying to get, no problem. I'm trying to get into this example in here, which is the fact that the charge, which is in joule, times the volt will give you, the charge which is in Coulomb times the volt will give you 1 joule. In other words, 1 joule, which is an amount of energy, by the way, is 1 Coulomb, which is a unit for charge, times 1 volt, which is the unit for the voltage. Okay. If I have 120 volt, if I take only 1 Coulomb, that means I'm taking 120 joules. 1.5 volt battery, like the one I was showing all day today, if I take 1 Coulomb from it, that is 1.5 joules from it. Obviously, if I keep on taking, I will run out of energy, and the battery I have to go replace from the store. Okay. Usually the balloon has a lot of charges in it, okay? But the reason why you don't see a lot of energy in this case is because of the fact that it's not discharging at the high rate. It's the current really that matters in this case, okay? Capacitor stores energy too. Capacitor stores charges too. Capacitor does that too. So you can charge a capacitor. I had. Where is my capacitors in here? Every electronic device, you can see them as this round thing, not in this example, at this round things in here, okay? Let me turn off the sharing thing quickly in here. So this is actually a capacitor in here. This is actually another capacitor in here. So those are the capacitors that store. Usually they become next to the power supply, and the power supply here is exactly this point in here. If you look at it, this is where you plug your device, and usually you have this capacitors to transform the current and actually protect the circuitry. There is one in here too. There are 2 in here, and there is 1 capacitor in here. So this is actually in every electronic device you have capacitors, and capacitors are useful in terms of storing energy and actually to protect energy. This is what kills you when they tell you do not put your hand in an electronic device immediately after you unplug it. Although you unplugged it from the wall and you think that you're safe to touch the device. No, you still have charge inside that capacitor. And you could close the circuit with your finger or yourself, and then the charge will run through you and actually can do a lot of damage, especially for big items like refrigerators and probably big machinery. It can be deadly. Okay, so those charges are very high. Okay, so this is how the capacitor works. You store energy in it, and usually they're used in actually in signals also. When you try to send signals, they're actually in AC current. They're used extensively too. Okay, there is another component actually in the trying to see if there is one in here. I can see quickly. I don't see it. Oh wow, we're gonna here. There is another component actually that can also do a lot of damage. That's this one. It's actually an inductor, okay? Inductor in here can also cause a lot of damage, so you don't want your hands to be next to them, okay? They're actually also here too, okay? So inductors also, but they don't store charge, they store current actually. And there is another actually a capacitor in here sitting on laying down. Actually, if you look at the value, you can actually see it too, okay? Fascinating stuff, electricity and magnetism, especially when it comes to circuitry. Okay, we're very close from the time being done in here. Okay, so I talked about the Van de Graaff machine, and this is how we build up charges in it. And when you stand, you have to stand on a neutral base. So if you go to a science fair or science invitation somewhere in there, and they don't provide you with a base to basically insulate you, you're going to be in danger. So you really have to be careful with it, okay? You have to really be careful with the Van de Graaff machine, which is a lot of fun to have. And I'm hoping that we go back. And then once we go back, we're going to demo that. And if you guys are around, you can come and have fun. Enjoy your spring break. Watch for messages from me concerning the exam, okay? And I'll see you guys. There will be no class after the spring break because there will be exam week on that day, midterm. So in other words, we will not see one another until basically what, 2 weeks after?
2 weeks from now or 2 weeks from the last Tuesday?
From last Tuesday. So
okay.
There will be a spring break, which is next week. And then the 2 days after that, which is the week after. So the last exam is going to be on the 22nd. That is when your exam is. So whatever date is after that, which is the Tuesday after, It's going to be the 27th. So we're going to meet on the 27th.
Okay, so 2 weeks from now.
Yeah,
From
2
Thursday.
weeks.
Yeah.
27th, man. That's a long time. It looks like the end of the month. Okay. Have fun. Enjoy your break. And I'll see you guys later. Okay?
Okay. See you. Thank you. Take care.
Have a good break.
Be safe.
Thank you. Let me stop the recording.